Welcome to all to this webinar of today. Today the topic is fluoride in groundwater and underground storage, and this is the 11th webinar organized by TheWaterChannel. It is the third in the series of webinars organized on the theme related to groundwater. We are really happy to have here two speakers, Dr. Seifu Kebede from Addis Ababa University, and as well Professor Redda Tekle Aymanot, as well from Addis Ababa University, from the medicine department. Both of them, they have a lot of experience in researching fluoride and its related problem. On the geochemistry side, Professor Seifu, and on the other side, on the health problems that fluoride has. So I will make a brief introduction, and I would like to remind that this webinars is also an initiative that is promoted by the UPGROW, that is a research program founded by UK. So fluorine is a natural element that is abundant in nature, but under certain conditions, it can lead to problems. In particular, if under specific condition in ground and surface water can exceed safety levels and became toxic for human health. The World Health Organization set as a standard 1.5 milligrams per liter. But if it is exceeding these levels, then it can cause dental and skeletal fluorosis. They are two biogeochemical diseases that they can really affect a lot of people around the world, and in particular in Ethiopia. However, in certain limits, fluorine can be also good for developing the bones, and as well to protect people from developing caries. Nowadays in the world, there are a lot of places where you can find content of fluoride that exceed this WGO standard, 1.5 milligrams per liter. And as well, UNESCO said that there are an estimation of 200 million of people that are at risk to developing skeletal and dental fluorosis. So thank you for being here. Now I will give the word to Professor Seifu to his presentation. Thank you, Professor, for being here today.
Okay, thank you, Sarah, for inviting me to this presentation. Yeah, it's raining heavily in Addis now, and I'm not sure if you can hear me. And this heavy downpour will affect also maybe my colleagues' arrival to this place. It may affect Professor Radda's arrival to this place. Yeah. So I will talk about genesis of fluoride, origin of fluoride in Ethiopian Rift Valley groundwaters in particular, and groundwaters in volcanic terrains of the Eastern Africa. As you can see from this slide, the slide shows fluoride content of groundwaters in different sectors of Ethiopia, and this data has been compiled by Ripple program and Meta. As you can see from the figure, in purple, the purple color shows the highest fluoride content, and that very high fluoride content in groundwaters is localized to the central part of Ethiopia Rift. Elsewhere, in higher areas in the plateau, in the in the northwest and southeast part of this map, you see relatively lower fluoride content, and which is still within acceptable limit, or even far lower than the WHO limit of 1.5 milligram per liter. So the issue now is, why is fluoride high in the Rift Valley groundwaters, in the volcanic terrains of Ethiopia? Next slide. Yeah. So now, the enrichment of fluoride in groundwaters has relation to the source of fluoride and then after fluoride is released from that source, how it is enriched in the groundwaters or removed from groundwaters. So the first reason as to why we have high fluoride content relates to the source. What is the source of fluoride? And second, I'll talk about how this fluoride is released from its source rock into groundwaters, and later on how it behaves once it enters into the groundwaters. The primary source of fluoride in the East African Rift volcanic aquifers relates to minerals occurring in acid volcanic rocks. This is an earlier view as to where the fluoride comes from. Minerals, particularly amphiboles, alkali amphiboles, contain OH radical, which is just here. I'll show you. In this mineral amphibole, this is an amphibole, and in this amphibole you have OH, and that OH has a size, smaller size. It is an anion radical with a smaller size and a charge of -1. So because fluoride has also similar charge, -1, and smaller size, it replaces OH in amphiboles, and it occurs, or amphiboles contain some fluoride. So this fluoride is later leached during weathering processes, and the fluoride enters into the groundwater. The issue here is abundance matter, meaning this mineral is not so much abundant in basic rocks, but is relatively abundant in acidic volcanic rocks like rhyolites, and it is compositional equivalent like ignimbrites, pumice, etc. The thing is, the volume of fluoride we have fixed to minerals is relatively lower compared to glass, volcanic glass, which occurs in association with the rocks or independently. Meaning volcanic glass make part of rocks, the ground mass in a rock. This is a photograph of microscopic view of thin sections of rocks from that region. Those bigger things that you see are, we call them phenocrystous minerals, but we have also very invisible, very tiny microcrystalline and glassy materials in between the phenocrystals. So this glassy material contain fluoride in diffuse form, or fluoride occurs feeling some defects in glass and defects in this microcrystalline ground mass. So this fluoride is later leached and enter into groundwater. So the relative proportion of contribution from volcanic glass has been proven to be the main source of fluoride in groundwaters. And a third source, primary source of fluoride, is direct addition of it from geothermal activities, particularly around geothermal areas. Because geothermal fluid, fluoride it is immiscible, and it doesn't form primary volcanic mineral, so it is concentrated in the later fluids during magmatic crystallization. So this fluoride is taken by volcanic gas along with other volcanic gas like carbon dioxide, sulfuric acid, hydrofluoric acid, and then this will join the groundwater at shallower depths. So direct addition. The thing is, we don't know as to yet what proportion of fluoride comes from the geothermal activities, geothermal addition, and what portion of fluoride comes from leaching of the minerals as well as the volcanic glasses. But the secondary reservoir for fluoride is from sediments. Sediments, and particularly volcanoclastic materials associated with lacustrine sediments. The sediments themselves are derived from the volcanics. So the sediments accumulate in the center of the Rift Valley Basin, and these sediments contain fluoride from the primary source as well as fluoride that is deposited in these sediments from groundwaters circulating within them. So these are the two main sources: primary source from volcanic materials and geothermal activity, the resources from the volcanoclastic sediments and alluvial lacustrine sediments. By no means primary and secondary doesn't mean the degree of contribution. It is only based on the genesis. Yeah? The primary source comes from volcanic minerals. Secondary source comes from alluvial lacustrine sediments. But the contribution from either of the two could be of similar proportion, or even the secondary sources contribute sometimes much more fluoride into the groundwaters. I'll come to this slide later. As you can see from this slide, the squares you see, the different squares you see here are geothermal areas. There are several sites whereby you have diffusion of gases and steam coming from the deeper mantle, and these fluids contain high fluoride, which directly adds into the shallower groundwater systems. But that we have the source doesn't mean that you'll have enrichment of fluoride in the groundwaters. So there is an additional derivative process that either enriches it or depletes fluoride once it enters into the groundwater. One control on fluoride enrichment is mineral saturation. By mineral saturation, I mean if you take groundwaters in the Rift Valley, most of these groundwaters have very low concentration of calcium and very low concentration of magnesium. This low concentration of calcium and magnesium by itself is as a result of loss of them from groundwaters as the groundwater moves from a recharge zone to the Rift Valley, which is generally a discharge zone for groundwater. The loss of calcium and magnesium is attributed to two processes. One process is calcium carbonate precipitation or carbonate precipitation in general, and the second one is cation exchange. Means calcium goes into the rock phase and sodium and potassium instead is released into the liquid phase, into the water. So we will have limited availability of calcium in groundwaters in the rift. This means fluoride will enrich in the groundwaters uncontrolled. If there was abundant calcium in the groundwaters, we will have saturation of saturation of calcium fluoride, and then eventual precipitation of calcium fluoride, and then we will have a cap, maximum limit on the concentration of fluoride in the groundwater. The thing is, we don't have enough amount of calcium and enough amount of calcium to fix fluoride. So fluoride enriches itself indefinitely. I mean, there are other processes that I'll talk later, particularly when it is related to lakes. So this is one source, saturation control. The saturation conditions with respect to carbonates and with respect to fluoride affects the enrichment of fluoride in groundwaters. Another process that could affect fluoride concentration is evaporation. I'll talk about this later. There is also correlational effect like porosity and permeability control, which I'll talk very soon. Here, for instance, this figure shows groundwaters taken from a transect from a highland in Ethiopia to the Rift Valley, all through the volcanic aquifers. As you can see from this figure, I'll show you here. Calcium calcium in groundwaters initially increase. This is from the highland to the lowland. As you go from the highland to the lowland and see the fluoride concentration in groundwaters. Initially it increases. Calcium initially increases as the rainwater comes into the rocks and leaches rapidly calcium and magnesium. Calcium content increases. But after a certain time, calcium decreases in groundwaters. So there are several models around this as to why the calcium is lost in the groundwaters. As I've briefly mentioned, it could relate to cation exchange or carbonate precipitation. There are two parallel running hypotheses about this. Cation exchange is taking place or carbonate precipitation is taking place, or both are playing a role. And then if you compare this against fluoride, which is the lowest figure here, the fluoride content increases against, opposite to the behavior of calcium. So that is the main control on abundance of fluoride in groundwaters. Geothermal addition, I've talked about this, and this slide shows, sorry, I meant to show here the control on fluoride distribution as related to texture of the rocks. You know, Yirgu in 1997, these are a group of researchers, have shown the fact that regardless of similarity in chemistry of the rocks, for instance, if you compare pumice, rhyolites, and ignimbrites, they are all of rhyolitic compositions. These are all acid volcanic rocks. Nevertheless, if you compare, for instance, groundwater in ignimbrites against groundwater in a more pyroclastic material like pumice, you get higher fluoride content in pyroclastic materials, pyroclastic equivalent of the rocks. They attribute this to control of porosity and permeability, meaning in porous volcanic clastic materials, you will have more surface area of interaction between the rock and water. You have large surface area for water-rock interaction, and thereby you have easy release of fluoride into pyroclastic equivalents as compared to rock equivalents. So in fractured ignimbrites, they have shown the fact that groundwaters contain relatively lower fluoride content. So this is regardless of the similarities in chemistry of these two groups or this kind of rocks in the Rift Valley areas. Sorry that you may not see this slide very well. I meant to show fluoride content in lakes in the Rift Valley, how fluoride enriches in the lakes in the Rift Valley. Here you see fluoride in lakes, and in the lower curve, here you see fluoride in groundwaters and thermal wells in the Rift Valley area. You see very high enrichment of fluoride in the Rift Valley lake or surface waters particularly. Why is this happening? Because as fluoride enters into the lakes from groundwaters or via surface waters, evaporation in the lakes will enrich fluoride, because evaporation will not take any other anions or ions, but fluoride enriches because of this evaporative concentration, and fluoride reaches very high values in the lakes. But the issue, particularly research in 1980s by Von Dam and Edmund, they have computed a mass balance for fluoride and other flux of other ions in these lakes. What they have done is they estimated the annual influx of fluoride into the lakes, and compared it against the volume of fluoride we have in these lakes. And if you divide the volume of fluoride you have in the lakes, or the quantity of fluoride you have in the lakes, divide it by it is annual inflow, that gives you the mean residence time of fluoride. Now, if you compare this mean residence time of fluoride with mean residence time of chloride, which is very conservative, a conservative ion, doesn't react except under special condition whereby you have evaporites. So the mean residence time of chloride is far higher than the mean residence time of fluoride in these lakes. This has been again proven in other lakes in the plateau in around Addis Ababa, meaning chloride stays more in the lake waters than fluoride. This means there is loss of fluoride somewhere in these lakes. Where it is going? So the initial proposal by Von Dam and Edmund in 1984 was that there is a reverse weathering process, meaning at high pH lake water, you will have formation of clay minerals. So along with the formation of clay minerals, the clay minerals absorb fluoride and sink it into the lake bottom. That is one possibility. Another hypothesis that was set was that diatoms in the lake, diatoms are silica secreting organisms. So silica binds fluoride as SiF6. So silica and diatoms bind fluoride and then sink it to the lake bottom. So that is why, regardless of the fact that fluoride concentration is high in the surface waters, in the lakes, it is not as high as it should be, because there is a sink for fluoride in the lake waters. So finally, I was very brief about the genesis. We can discuss following this presentation. But what does this mean for safe sourcing of fluoride or low fluoride containing water in an otherwise high fluoride zones? For instance, one thing that we could do, yet to be proven, we have limited data on this, is instead of tapping groundwaters from alluvial lacustrine sediments, isolate the alluvial lacustrine sediments and drill into the bedrocks, and the bedrocks could contain low fluoride content. There are some drilling activities which are kind of indicative of this, but this has yet to be proven. Second is target rapid through flow aquifers. And because rapid through flow aquifers, meaning if you have high recharge, rapid velocity, groundwater flow velocity, and the interaction time between the water and the rock is reduced, then you may have low fluoride content. For instance, we have volcanic ash in the highlands, in the Ethiopian highlands, several places, but the volcanic ash in the Ethiopian highlands contain relatively lower fluoride content compared to volcanic ash in the Rift Valley. This is also indicative, meaning in areas whereby you have high recharge, rapid through flow of water, groundwater, then your fluoride content could be lower. Another thing that we could look into is into the facies, different sediment facies in alluvial lacustrine sediments itself. Because the research, past research have shown that the main source of fluoride relates to volcanic glass. If you target the alluvial lacustrine sediment zone, whereby you have lower concentration of volcanic glass, where it is teared and weighed down because of, for instance, different alluvial aquatic sediment zones should have different energy conditions, water energy conditions. So these water energy conditions may lead to different degree or different proportion of these materials. So we can look into this kind of, this is what we are looking currently into, this possibility, different facies zones in alluvial aquatic sediments and groundwater fluoride concentration. The last point could be, by the way, evaporative concentration is not only taking place in open water bodies, in shallow aquifers, in the shallow alluvial aquatic sediments, you can have, in this arid, semi-arid setting, you have evaporation directly from the aquifer because the sediments are coarser, and then the evaporation could go down to tens of meters. So this evaporation, which is taking place directly from the aquifers, enriches the groundwater in shallower underdug wells. So depth-wise, how is it varying depth-wise? This is one thing that we could look into. So thank you very much. This is my brief presentation, and yeah, thank you.
Thank you very much, Seifu. Um, this is Abraham. Thanks for your presentation, Seifu. There is a question which maybe you would like to address at this point, or if you want, we could also move it to the end of the presentation. But if you notice in the box below the slides, there is a question from someone called Abe. And the question is, in the Western world, fluorine has been introduced in the water supply systems for a long time, and supporters of this practice point to the positive health effects, while critics point to the negative effects of excess intake. And the question is, how can this be considered a bad idea? Because when fluoride is being artificially added to a water supply system, it is essentially a controlled process. So, is this a question that you would like to address at this point?
Yeah, if there are other questions, I would like to answer them in totality.
Okay, then we can move on to the next presentation, which is by Sarah, and we will take up this question at the end of it, along with the other questions that might have come in by that time.
Okay. How long did it take me?
Wait.